Excellent. So thank you, Andy, for a nice introduction. So I will give a talk today about mixed mode bending tests we have performed in our laboratory on structural adhesive joints using a dual actuator load frame. And the agenda is a little bit like in a classical way. I will give a short introduction, then I will talk about the theoretical background and some stability criteria. Then I will give some information about our experimental setup and show the results, and then the summarize up. Like in the beginning, I think the mixed mode bending test is well known, and usually it's done using a load jig. Instead of using the load jig, we applied 2 actuators, and the idea was the setup was to have, let's say, as much arbitrary loading on the specimen so that we could be able to change mode mixity during testing, or to test or to control the test on something else, like say on constant mode mixity or whatever. And therefore we call the test a controlled mixed mode bending test. To be honest, I have to summarize that it's not the only dual actuator test available for this kind of stuff. I think the one at the bottom, I think it's well known for some of you. It was developed by Dave Dillard's group, I think already a couple of years ago. And it's a little bit like a combination of an ENF and an ELS test, while our test like the MMB, it's more like a combination of a DCB and an ENF. Oh, sorry, the lower is a DCB and the ELS. And in the upper case, in our, we have the benefit that we can use J-integral methods. So we can use forces and rotations to evaluate fracture energy. But in the lower parts, we have a little bit of problem that we have this fixed clamping at the bottom. And fixed clamping is firstly hard to realize in an experimental setup. And the second one is coming with this ELS effects. We have to do some clamping calibration, this kind of stuff. And always, if you're using this lower kind of setup, we have to do some kind of compliance calibration, which we can do for the upper one, but we do not have to do it for the upper one. But to be honest, also the lower setup has this changes and this advantages. And actually, the guys in France, the group of Julien Jumel, they're always now dealing with this kind of setup. And hopefully in the future, we will be able to compare our results to theirs. So we will see. Okay, coming a little bit to theoretical background. There are several ways to evaluate this test. I just will here refer to J-integral, which is based on measurement of forces and rotations, and later on linear fracture mechanics employing the Irving-Keyes equation. Actually, what here is, or should be valid, is the first one, is the equation for the total J-integral. So really sure that this is valid for this kind of specimen. Everything below here is some kind of mode partitioning, which works in this case that we partition the displacement on the specimen into a symmetrical DCP part and an asymmetrical ENF part. But I think with respect to those of you working on mixed mode behavior, mode partitioning, it's a really difficult thing. So we rely here on this really global approach to do that stuff. The second point is just an evaluation on the Irving-Keyes equation. So one has to calculate the compliance matrix. And then, of course, it's possible to calculate the mixed mode ratio just in terms of the ratio between the forces. There's linear interpolation between these two. But in this case, somebody has offshore to calibrate the entire compliance of the specimen. Okay, one thing which came in mind, not actually before we planning the tests, but during doing them, was the question of stable crack growth. I think it's rather known that the DCB and an ENF test is definitely unstable if it is operated in force control. And in displacement control, at least in case of the ENF test, it depends on which crack lengths we have, while the DCB is always stable. And we put it into some, let's say, square root of J control, the actuators, to keep mode mixity constant. And of course, we did not consider at all what will happen with stability in this kind of tests. So actually the motivation of this was that we are triggering out our PID parameters. We were completely happy that the tests were running. And we had a look, and then if the crack started to propagate, it turned unstable, and we damaged, I think, at least 1 or 2 load cells. And so it was just a motivation to add here this kind of stability criteria. The left one is actually chosen for a way that we operate. So have a look. That we operate this, going back, this left actuator and displacement control, and keep the mode mixity with the one in the middle. In that case, we can achieve some kind of a stable region, and we designed the crack lengths to be sufficiently large. And in that case, if we choose this kind of geometry, the crack will propagate unconditionally stable. But okay, it will not work for pure mode 2 or really close to mode 2, but it will be stable until we get really close to mode 2. In the other case, if you're coming from mode 2 and using this, let's say, DCP actuator to control mode mixity, we will run unstable as soon as we're coming too close to mode 1, and it also gives some kind of verification after that. Okay, this is our experimental setup. I think people are usually judging me for having this really huge samples, but this is just for the reason that we have really tough adhesives inside, and we have to avoid plastic deformation in the beams. But actually, we can scale it down. But in this part here, we were rather happy to have this large specimens because it was a little bit easier to mount. What we see here is a classical servotolic testing machine with the stroke here in the middle. And on the right, on the top, you see an electric actuator, which we just use in the same control loop to operate the tests. Okay, also in the title was something related to optical fibers. I honestly have to say I skipped them a little bit here of time. Just keep it like an, let's say, continuous strain gauge with a spatial resolution of approximately 0.5 millimeters. And by the maximum strain, we detected the position of the crack tip. There will be 2 presentations of my group giving today in the same session by Leah and Lucas. And they will have the same measurement, so they will tell a little bit more about that. So here we keep it just to identify the crack lengths. And yeah, just we'll show our results on 2 adhesives. The first we have using to prove the method, and on the second one, we had the intention to test the dependence on the fracture envelope on the adhesive layer thickness. Actually, when coming to the results, this is also really interesting part, because if we have now a compliance matrix, of course, we have to determine that in an array. And what we did was that we load the specimen in mode 1 to provoke a little bit of mode 1 fracture. Then we change the loading a little bit like this, to have the possibility to have a load vector and a displacement vector which are not linearly dependent on each other. Or we can calculate by this way the compliance matrix like arbitrary. So we did it in approximately, I think it was 300 loops running for approximately 2 days. Run test, and we performed 2 tests. The matrix NTC to 2, it's really easy to determine. It's just a cubic root of the compliance versus crack length, and you can use a linear regression. On the left-hand side is a little bit more difficult, because there's also the span length here needs a correction in the ENF part, but it's also, I think it's well published also at Imperial at the end of the 80s, I guess, since by Gordon Williams, which just a classical procedure to get these parameters. One interesting result are here, if you're looking at this stability criteria. On the left-hand side, you see that in the logarithmic plot, the crack velocity we determined, and dependent on a mode mixity in tests we run at constant mode mixity. And as a test for all quasi-static, you see like the dots which have been in this first control mode, they were unconditionally stable, and we realized mode mixity is up to 80 degrees, really close to mode 2. On the other way back, we run unstable here, approximately about 70, 65 degrees. The velocity jumps up, so we have the unstable region somewhere here. And our calculation told us if we consider corrected beam theory, which is a blue curve, and the dashed line is our initial crack length, so then we expect unstable behavior here at approximately 67 degrees. So this fits then very well to our prediction. Okay, these are now already the fracture envelopes and two kind of, let's say, plots. On the left-hand side, to see a classical plot where we plotted J to C over J1C, with crack initiation and crack propagation values. On the right-hand side is a little bit more interesting, like from my point of view, because we see also that we do not have an influence on the control mode, which is good, like in the end. It doesn't matter how we run the test. But also the drawn lines, which are the blue, the cyan, and the green one. There are tests that are operated completely in displacement control. And the idea was to change the mode mixity during the crack was running. And we really see here somehow, of course, within the scatter, some good agreement between the results. Even if close to mode 2, we had a really, let's say, increase in scatter for some reason. And we had less scatter here close to mode 1. On the next slide, on the left-hand side, there are the R curves. I think they are somehow completely flat, so there's nothing very special into there. On the right-hand side, this picture is a little bit more interesting from my point of view. Like the blue dots are the tests we have performed in this study. And the green and the cyan ones were ones which have done in France on the same adhesive, which are different kind of tests using MMB and the Arcan test. So we use them from literature as a reference. And this is, of course, agreeing with ours. So this is first good. But then the most interesting part, the red dots, are something we did in our group on mixed mod 1 plus 3 on the same adhesive, but with a completely different setup. But we observed the same fracture envelope. And this is something I personally think really interesting, that with different methods and different kind of mixed modes, we achieved the same fracture envelope. And of course, it remains the open question if there's no distinction necessary between modes 2 and 3. This is at least an indication for that. Okay, so finally now the results for the second adhesive, where we applied, I think, 5 or 6 adhesive layer thicknesses, and we want to see a dependence of the fracture envelope on the adhesive layer thickness. And what we see here is simply no scatter, so we have no tendency, and at least we see it here in the right-hand side plot. The fracture energy seems to be somehow constant, and then it jumps up at a mode mix ratio of approximately 50 degrees. So having a closer look at that, we found out that this region has a completely cohesive fracture pattern up to 50 degrees mode mixity. And afterwards, it tends towards adhesive fracture patterns. And this is a quite interesting result, because from other adhesives, we used to have cohesive fracture in DCB tests, and let's say adhesive or partly adhesive failure in mode 2 tests, like we used ENF or tapered ENF. So here we at least get some kind of transition zone where we get a transition from the cohesive to the adhesive fracture without judging for the reasons for that. It's just an experimental observation. Okay, so this is just the summary. I think the most important here is that we had fracture envelopes involved, matching also results in mixed mod 1 plus 3. And the last point is also interesting, but it's really weakly formulated. Like we may use the test to get further insights on the path dependence of cohesive laws. So I do not aim here to identify cohesive laws using a potential-based model, because I just do not believe in that. So I think there's much more work have to spend into that point here in the future. Okay, that's the end of our presentation. For further reading, I would refer to that publication. We just concluded QR code, and we did also further evaluations of the fracture energy using Williams' method and this optical fibers. I just skipped that here for keeping the time, which I just did on the minute, hopefully. Thank you.